To start with, I think a few words on the DLR are in order. The DLR provides specific functionality that is specifically designed to meet the needs of dynamic languages. For example, there is support for a shared dynamic type system. There is support for a shared hosting model. There is support to generate fast dynamic code and fast symbol tables. And you never need to write things like a garbage collector or IL generation or method caching. The availability of such shared functionality means that the language developer on the DLR can focus on features that make his language distinctive. You don't have to worry about all of the other heavy lifting that you typically need to do because the DLR does that for you. So you can worry only about those features which make your language distinctive. And that is what this talk is about. Prototypal inheritance is a distinctive feature of JavaScript. And I'm going to talk about how we implement that in managed JScript on the DLR. So here is some script code. We set a property on an object's prototype. We construct the object using new, and then we get at the property through this constructed object. The property itself, x, should actually now be fetched from the prototype. So in prototypal systems, objects inherit from objects. In other words, the prototype of an object is by itself an object. In the case of JScript, when we construct an object, we stash away a hidden link to this prototype. Now when a member is looked up on an object using either the dot notation or the subscript notation, if that member is not found on the object, then we examine this linked object. The linked object in turn could have a similar link. So this prototype chain, so to speak, is looked up. If the chain is exhausted, then we return the value undefined. That is the defined behavior in JavaScript. At its simplest, a language implementation should generate a DLR AST that represents the computation that it wants performed. So this computation could be in the form of actions. Get this member, add these two values, call that value, so on and so forth. All of the interactions between the language engine and the DLR happens in the form of trees, and each of these actions that I was talking about is actually represented as an action expression, and the DLR associates a dynamic site with such action expressions. So let's look at what happens first. What is the JScript AST that is generated for the code that I just showed you? So for just o.x, the JScript parser translates it into a qualified expression, with o being the base and x, the identifier x, being the qualifier. Now in the code generation phase, this JScript AST that I just showed you is translated not into IL but into a DLR AST. So every action that we want performed is mapped to an action expression, and this action expression encapsulates the action that needs to be performed. In our case, it's a get member, and the argument on which the action needs to be performed. And there comes the first oddity with JavaScript. So in the example I showed you O.x, where we tried to access the member X on O, but JavaScript actually allows you to do 1.x. Under the hood, there is a boxing operation that happens, and the 1 is converted to a JavaScript number object, and through that, this X on the prototype is now accessible. So rather than have the DLR exposed to such oddities, we plant our first hook. So the language processor actually hands off a DLR AST for execution, right? In the process of handing over this DLR AST, the language engine can choose to plant hooks that get called back. This is the occasion where we plant our first hook. Now the argument on which the action has to be performed, the argument on which this get member action has to be performed, is the result of a method call expression. And we hook that and redirect it to a API in the JScript runtime that we provide called convert.toObject, which does the necessary language specific operation. In this case, it just boxes it to a JavaScript number object. So we saw action expressions which encapsulate an action that needs to be performed on some argument. For each for action expressions, the DLR associates something called a dynamic site. And a dynamic site encapsulates the action itself that needs to be performed. In our case, it's a get. The dynamic site is an invocable entity, and the arguments that you pass to it are the arguments on which you want the action to be performed. That the action is a get member using the symbol X, all that is captured in the dynamic site itself. The first attempt at invoking it causes a callback into a DLR function, which is responsible for generating code to execute the action. Okay. Once that code is generated, the dynamic site's target itself is updated to point to this newly generated code. Okay. So in our case, you'll notice that the hook that we planted, convert.toObject, is actually a call into a JScript runtime API. So what happens when you first call an invoke on a dynamic site? The control goes to a DLR entity called an action binder. And the action binder is responsible for being able to generate code to execute the action. Now in our case, the action is get member. Now, how can the action binder know to perform any language specific rules? Can it? It cannot. In order to remain generic enough, it delegates the task of generating a rule to a language specific component. In order to be performant enough, it then caches this rule, so that the next time if there is a similar request for an action on a similar set of values, it knows that it already has the rule with it. It need not go back to the language specific component to ask for a rule. Okay? So in our case, the action binder delegates the creation of a rule for get member to a language specific component, which will be a JS object, which is again living in the JScript runtime. So how does it know to delegate to a language specific entity. In our case, it knows because the JS object that we provide registers itself with the DLR, saying that it can support a particular interface which is called iDynamic object, which indicates that the JS object is capable of generating rules for actions that need to happen on itself. Okay? So all that the action binder does is it looks up the getRule method and calls it. And off we go at this point into the JScript runtime. And what does the JS object do, which is in the JScript runtime? It implements the iDynamic object interface, which is a very lightweight interface which has only one method. It's called getRule. And in our case, what is passed in are details of the action to be performed, an execution context, which will have the scope chain and others, and the actual arguments on which to perform the action. In our case, it will be O, because on O we are doing the action of getting a member. So now the JS object has to generate a rule and return it to the DLR. Now the rule here is to get a member, right? Now getting a member in the case of JavaScript is a little bit complex. You might have to walk the prototype chain. You might want to do certain specific optimizations, whatever. So this is the time when we plant our second hook. Remember, the first hook that we planted was for this boxing, the automatic boxing that we wanted to do during the invoke. This is the time when we plant the second hook. So the hook that we plant is to a method called try_getItem, which is again on the JScript runtime on the JS object. And we pass to try_getItem X, which is what we wanted to get, and a temporary variable. The return value of try_getItem, which is Boolean, we use that to decide on whether to take the then clause of the if statement or the else clause. Now if we take the then clause, then the looked up value of X is returned in the temporary. If we take the else clause, then we call get failure statement, which in turn will return undefined, which is JavaScript behavior. Okay? So this is the rule that we return to the DLR. The rule itself is in the form of a tree. There is a condition, which is the call. There is a then clause, which is the make return, and there is an else clause, which is the failure statement. So you'll notice that the rule itself is comprised of a test and a target. So the test basically ensures that the rule is never run on anything that is not a JS object, which makes sense because we are after all generating rules for JScript. So the test just ensures that we never run the rule on anything other than a JS object, and the sorry?
Can that test ever fail, given that you inserted a cast in the...
The test can fail if the arguments that are... So this test will be specific to the kind of types of the values that come in. At a later point, if the values change, then this test is likely to fail. So we'll come to that and how that it gets updated. So there's a test part and the target part, and the test ensures that the rule, that the target never gets run on anything but a JS object, and the target does the actual work. And in the target, we actually again planted a hook into the JScript runtime. Now the DLR generates dynamic code for the rule that we return. So if you look at it through the reflector tool, if you view this using the reflector tool, this is how the code looks. So you'll notice that there is the test and the target, and then we have planted the try get item call. So try get item is just a callback into the JScript runtime component that we ship. And if we don't get the if the lookup fails, we return undefined. And then there is this call at the bottom, update binding and invoke. This will be called if at a later point this rule gets invoked with arguments that fail the test. If it gets invoked with arguments that fail the test, it will just fall through all this and it comes here. And when this gets invoked, the action binder initiates rule generation afresh and then updates the site based on the newly generated code for the rule. So this is how the generated code looks for the rule that we have. And so finally we reach try get item. So try get item is what we planted here, right? Which is a JScript runtime function. So finally we reach try get item. So in try get item we are now going to do the actual member lookup. So in here what we do, we look up the member in a property bag that we have, which is underscore properties. If we get it there, then all is well. We can return the property. If we don't get it there, then JavaScript rules require that you walk up the prototype chain. So remember when we construct an object, we stashed this link to a prototype, right? So we use that and now we recurse up the prototype chain doing a try get item. So we'll try and look up the member on our cells, else on our prototype, else on prototype chain throughout. If we still don't get it, sorry.
What happens if an intermediate prototype is updated in between when that rule gets inserted? So if, for instance, you didn't have the member value on the first one, you check the second prototype. The second didn't have it, so you check the third, and you found it there, and you inserted it there. Following so on?
If at the time of lookup, if the member is not found along the prototype chain, we will return an undefined.
Okay, but if the second prototype is updated, and now that member now lives in the second prototype, so if it was following the chain,
Yeah.
you would find it the second, but you have cache the third.
Oh, so you mean you passed one of the objects where the members are found?
So yeah, you cache the third one, right?
Yeah.
And then after you cache the third one, the second prototype is updated. It's possible to do that in JavaScript at runtime, isn't it? Update a prototype.
Yes.
So if that second prototype is updated, and the member that was found and cached in the third one now exists here, it's now returning a cached version instead of the middle version.
I'm not sure I'm following the question. Okay. Yeah.
It does look like there's a race condition there if the prototype is set null.
And if we still don't get it on the prototype, then we return undefined, which is what is the JavaScript. So if we see the flow, of how we go about implementing this, we start with creating a JavaScript AST, translating that to a DLR AST, and in the generated DLR AST we plant hooks because we wanted boxing to happen. For example, we generate the DLR AST and then it goes off to the DLR. Dynamic site is created and invoked because a dynamic site is an invocable entity. It is invoked. In the process of invoke, our hook got called and we did whatever was the language specific operation like boxing. Then the rule is sought for by the action binder because it can't possibly figure out what is a language specific rule. it comes back. We had registered ourselves with the DLR, implementing iDynamic object, saying that we are capable of generating rules for ourselves. So we get back control. We generate and return a rule. But again, in this rule, we plant a hook because we want to actually implement the semantics of prototype chain walking. So we generate a rule and return it. Again, the dynamic site is updated, and this time when the invoke happens, control comes to our hook, and that's what this was the try get item API. And at this point, we are able to look into our own property bag or walk the prototype chain. So this is the flow by which we have been able to implement prototype-based lookup in the managed JScript on the DLR. And that's about all I have. So we have a blog on MSDN, which I invite all of you all to come and take a look at. And my name is Pratap, and I'm on the JScript team. Yeah.
I think I understand what he was asking. I had a similar question. So the thought I have is if you are in the process of looking for the appropriate rule, or you're regenerating the dynamic site, you're going to try and update it, correct? Mm-hmm. If you get to a point where you are satisfied that you have the dynamic site you want to update, but while you, in between that time, another call comes in and finds some new result, and it does an update of what's actually the correct dynamic site with the correct information, you end up overwriting that with old information. Is that correct? So there's a period of time where you may actually damage a correct dynamic site because you're inserting it later than the correct path did.
Is that possible?
I don't think so. I think your rule targets work for 0 or more prototypes.
So what I don't say there's a performance hit that you can potentially get from updating a site with older information and overriding somebody who has some newer information in it. And we've realized that performance hit is there. There's no correctness hit. So the good news is that if you update it with old information, you might invalidate a site 2 or 3 times rather than invalidating it once. As we looked at that, it was a choice between that or having a complicated locking architecture around updating the sites, and we're pretty sure, and we'll be spending more time, that we do have a lock-free, very fast architecture for updating the sites. And having that lock-free architecture we felt was worth that risk of potentially updating something 2 or 3 times, so long as there isn't a correctness risk as well.
There's one other option that might be reasonable. This is how I did it in JRuby. I can speak up. Okay, here we go. So I wanted to avoid a lock. I wanted to have a lock-free caching architecture as well, but I also wanted to avoid checking guards every time completely. And so all the call sites actually register themselves into the type model. And when the type model updates in specific ways, it goes and invalidates all of the sites that say that I've cached this particular information. So then you're able to avoid you're able to avoid having to lock when you do the updating, and you are able to avoid doing the guard check every single time you run through the site.
But in your approach, have you had a performance issue?
No, not really, because the call actually goes through without ever hitting a guard, because the changes are pushed out from the type model rather than pulled in as part of a guard.
So maybe we should talk about that in more detail. We looked at exactly that architecture. We decided not to do it because of 3 reasons. Okay.
It's for the recording. That's it.
Yeah. So we decided not to do that. We did have 3 reasons, but I'd love to find out if they were the right ones. One of them was the memory overhead of that additional caching. We were worried about that with a lot of dynamic sites in the world. Another one was that performance hit. Every time you made a dynamic change, you potentially had a large number of call sites you needed to go out and hit, many of which may never be called again. And the third reason was the threading, quite frankly. And we were really worried about getting the locking right on that update process. And our analysis of it said there was going to be some potential race conditions between that update process and the call. And that was the killer of all three of them. And that's the one that, if there's a good way of avoiding any of those race conditions, the updates might be interesting.
We can talk later about it.
All right. Thank you very much.